Okay. So we are going to finish up chapter 12 today, and I had several questions over the last couple of days about the regression equation and calculating that and calculating values based on the regression equation. We're going to do all of that today. And we're actually going to do together a couple of problems that are in your homework. So in sections 12.1 to 12.3 and 12.6. So we're going to look at a couple of problems there. So on Monday, we had put this data in our calculator. I get rid of these. And this is the data that compared the score on the third exam in a statistics class to the score on the final. And we put that in our calculator, and we had run a linear regression t-test on this data. So let's do that again, because I want to bring that data back up. So I still have my data in L1 and L2. So I'm going to go to my stat menu, over to tests, and I'm going to find the linear regression t-test, which is F. And I'm going to run that again on L1 and L2. I'm not worried right now about beta or rho. If I were to be conducting a test to test the strength of this linear relationship, I can do a beta test or a test on rho. So that is the Greek letter beta. That's the Greek letter rho. It looks like a P, but it's rho. So I could do that, which we will do in a little bit. But I am going to do something I didn't do on Monday. I'm going to store my regression equation in my calculator. So your calculator is going to calculate the regression equation for you, the y-intercept and the slope. But I want to store that in my calculator because I'm going to graph it. So I'm going to go down here to where it says REGEQ. And I'm going to go to a menu we haven't been to before today, but holy cow, is it a pretty special menu. And it's the variables menu. We've been going to the distribution menu, which is above the variables menu, but we haven't gone to the variables menu yet. And just to show you on the first screen, all your statistics variables are stored in your calculator. So if you run a regression, or you run a t-test, or you run a z-test, or any kind of test, it stores all the statistics for you. And you can recall them from the statistics menu. We're not going to do that because we want to take that regression equation and we want to put it in our y equals so we can graph it. So we're going to go to the y variables, the second menu. And we've only been using functions so far in any course that you've taken. I don't know if you've taken trig yet, but we're going to go to function. And we're going to store that in y1. So in our y equals menu, it's the first equation. So I'm going to hit enter. And when I go back, you can see that it's now going to store my regression equation in y1. And then we're going to calculate. So it does give me the regression equation y equals a plus bx. A is negative 173.513363. That is the y-intercept for that particular linear equation. And the slope is b, 4.8273942009. And it gives me a standard deviation and it gives me some other information. So I'm going to arrow down. It gives me something that's called r squared. That is called the coefficient of determination, I can speak, which you're going to have to put into the box in my open math in several places. And the next one is R, and R is the correlation coefficient. And R tells you how good a fit your data is to a straight line. 0.66. Okay. All right. So that's the information that comes from running a linear regression t-test. Okay. Now we graphed the scatter plot on Monday. Now when I graph it again, it's going to graph the scatter plot, but it's also going to graph the regression equation. So let's go to the y equals. Y equals. Do you see your equation and your y equals now? So you've stored the regression equation that was calculated for you in y equals. So I'm going to go back to my stat plot, and I'm going to make sure that I'm still plotting L1 and L2, which is where I put my data. Still good? L1, L2. So now I'm going to hit zoom 9. It's going to graph my scatter plot, and what's that outline? That's my regression line. Okay. So can I use the regression line to predict the score that someone makes on the final if they made 90 on the third exam? No, they can't make a 90. It was only 80, wasn't it? 79? So you might have noticed that I have to be careful what I use my regression line to predict. It can obviously only predict for values that are in the domain or in the values for your independent variable. So what's the lowest number of my independent variable here? 65, is that the lowest? So I can't use this to predict someone what their score will be on the final if they make a 50 on that third exam, because that's not in between my lowest and highest data value. So I can use it to predict anything in between the lowest and the highest, but I can't use it to predict anything smaller than that. So what did I say, 79? Can I use this to predict what someone would make on the final if they made a 79 on the third exam? Sure. How do I calculate what that value is? I'm going to do it by hand. You got 2 ways to do this. Above your trace button is the calculate button. Number 1 is value. It will calculate Y for any X you input from your regression equation. It will calculate, it's called Y hat. So when you calculate, I don't think it there too fast. Okay, when you calculate a predicted value from your regression equation, it's called Y hat. Okay, so if I want to predict what someone would make on the final if they made a 79 on that third exam, type in X is 79. That's out of my range. That's what it's telling me. So my window is not quite big enough. So let's change our window My Y max is 76, so it told me it was out of range. I'm gonna make that 80. And try this again. Okay, try this again. So I'm gonna go my calc menu, value. Now try 79, and it should work. So 79 must be out of my, really out of my range, because it's saying somebody's gonna make a 207. I think the exam was only worth, what, 200? So maybe that wasn't the best value to pick for my predicted value. But I can also go to the table. So if you go second graph to the table, look at that. It gives you all the predicted values for a particular X. So if I want to know what X is 79, I can just arrow down. It takes me forever to arrow down. Maybe not the fastest way to go. You can also do a table set so that it sets the table in between values you want. Even though it's out of the domain, you know, if someone made a 50, oh, it's going by a 66, 67, 68. I hit too many. Hit the arrow way too many times. But you can see scrolling through. So for a particular value of X, what did I do? X is 79. So I'm going to go back up there to it. Go 7.5, is that what we calculated? So that's two different ways you can find the predicted value of Y from your regression equation. Okay? So on several of your problems, it says, what would it predict if X is blah, blah, blah? Just let your calculator do that for you. And it's effectively taking that X value, plugging it into your regression equation and finding Y hat. Y hat being the predicted the value that your regression equation predicts for Y for that particular input X. Okay. Now, some other information that was on there, and I talked, you don't care how to calculate your regression, is R, the correlation coefficient. Is that an ugly enough formula for you? So does your calculator calculate R for you? And the answer is yes. So what does the correlation coefficient mean? Well, the correlation coefficient can range from -1 to +1. The closer it is to -1 or +1, the better the linear relationship. The better that your regression equation can predict. So the closer it is to 1 or -1, the better you are as far as your regression equation goes. If R is 0 or close to it, that means that there is no linear relationship between your two variables, so you can't use a regression equation. If it's 1, that's perfect linear correlation. If it's negative, and the slope of that line would be positive, so the sign of your correlation coefficient corresponds to the sign of your slope of your line. If R is -1, that's a perfect negative correlation, so the slope of your regression line would be negative. Okay, so if you have a strong linear correlation that's positive, you're going to get a larger R. It's going to be closer to 1. If you have a strong negative correlation, which is the second image there, then you're going to get a value of R that's closer to -1. And then if there's no correlation at all, 0, that means you're not going to have y depending on what x is. A horizontal line, y doesn't care what x is. A horizontal line, y is constant. It doesn't matter what the independent variable is, y is a constant. Okay, as a reminder, boy, howdy, would it be nice to tell researchers this. Just because there's a correlation between two variables, and it's a strong correlation, does not mean one thing is causing the other. This is real data. This is an actual scatter plot that shows the correlation between the murder rate in New York City and the sale of ice cream. As the murder rate goes up, so does the sale of ice cream sales. Do you think that ice cream sales are dependent on the murder rate? Do you think that the murder rate causes what did they do? Kill somebody and go out for an ice cream? What do you think is causing this? Is there another variable involved that's causing this? What's that?
Nicer weather.
The weather. People kill each other more when it's warm. I don't know if that's because you get angry when it's hot, no air conditioning. I don't know what it is. That's what it is. The confounding variable, the underlying variable that's causing this is, this is an infamous example. Every statistics teacher uses this example. All right. So that R squared is called the coefficient of determination. R and R squared are related to each other. R is the square root of R squared, or R squared is R squared, however you want to think about it. So what is the interpretation of the coefficient of determination? When expressed as a percent, which is what we normally do, one of your problems in my math lab says, what is the coefficient of determination? And they put a percent sign symbol in the problem. They want you to write it as a percent. Represents the percent of variation in the dependent variable, y, that can be explained by variation in the independent variable, the explanatory variable, x, using the regression best fit line. So because you have a regression best fit line, as x changes, so does y. Makes sense? And the amount of variation that you get in that difference from the regression line to the data is the coefficient of determination. And 1 minus R squared is the percent of variation that's not explained by the variation in x using the regression line. See, you've got, well, we're going to talk about residuals in just a second. The data that you collect and the predicted value of y from your regression equation are not going to be the same thing unless your correlation is perfect. If your R is 1 or -1, you're going to get some variation in the difference of your predicted y value, what your regression line predicts, and what you actually collected. Okay, so on our example that we ran just a minute ago, the third exam score versus the final exam score, we saw that the equation of best fit, that regression equation is -173.51 plus 4.83x. So they give me in my information, they give me A is the y-intercept. They give me B is the slope. They give me the correlation coefficient R, 0.6631. They give me the coefficient of determination, which is 0.4396. So the interpretation of the coefficient of determination is approximately 44% of the variation in the final exam grades can be explained by the variation in the grades on the third exam using the regression line. Okay, what's a residual? A residual is the difference in the predicted value of y from your regression equation and the y that you actually collect. So you're collecting data, you collect x's and y's, you draw a scatter plot, you get a regression equation, and your regression equation predicts values of y for a given x. That may not be the x that you and y order pair you collected. So residuals are obtained by performing subtractions. All that we must do is subtract the predicted value of y hat from the observed value y for a particular x. The result is a residual. And then what you can do with these residuals is you can graph them versus the independent variable. So you graph the independent variable on the x-axis and the residuals on the y. And if there's a predictable pattern to this, if there's a pattern involved, then you cannot use a linear regression. If it's just scattered all over the place, you're good to go. So you have that one problem in section 12.6. It's yeah, this one. So of these 6 graphs, which one can you do a linear regression on? Not B. Why not? Can you see the pattern here? You get this V pattern. If there's a pattern in the graph of the residuals versus your independent variable, you cannot use a linear regression on it. You see a pattern here? Something. You see a pattern here? Again, we get this kind of V shape, and then we get stuff down here. Definite kind of an H pattern there, and a linear pattern there. So none of these 5 can you use a linear regression on, because there's a pattern in the residual. So the only one you can use a linear regression on is what, A? So I think it says, which one can you not use a linear regression? What's it say? Select all the charts that violate. So everything but A, correct? I think I got that one right, didn't I? Oh, I did. How about that? All right, more on residuals. The formula for residuals is straightforward. The residual is equal to the observed y, so the data you collected, minus the predicted y, the y that comes from your linear regression equation. So the residual is y minus y hat. It's important to note that the predicted value comes from our regression line. Y hat comes from your regression line. The observed value comes from your data. All right, so this is a problem that shows up in both homeworks. And this is the number of stories in a building and the height. Okay, so we're going to do a couple of different things on this problem. We're going to put this data in our calculator. We're going to run the linear regression test on it. We're going to look at the residuals, and then we're going to run an actual hypothesis test on it. Okay, so give yourself a minute there and put that data in your calculator. And I'll show you how to find all the residuals. Okay, you got it in there? I put my data in L3 and L4. So the first thing I'm going to do is draw a scatter plot of this. So before I do anything else to go to all this work, I'm going to draw a scatter plot. So I'm going to go to my stat plots, number 1, and I'm going to do a scatter plot on the list where I put this stuff, which was L3 and L4. Okay, good to go. Now I'm going to do a zoom stat to set my window. It's pretty linear. So it looks kind of linear. I think I'll do a linear regression test on it. Okay, so I'm going to go to my stat tests, find F, linear regression t-test, and I put my data in L3 and L4. So I'm going to change that, but you see it's still storing my regression equation in Y1, so that's good. Okay, so calculate. I have to calculate it so that it will actually graph it for me. All right, so the regression equation, some information here that you might want to make note of. The t statistic for this, by the way, you have the same data in your problem. Make note. We're working the problem together. So the t statistics 8.05911. The value, p-value is practically 0.0000207. Degrees of freedom is 8. You don't really care about that right now. The y-intercept is 102.4287. And the slope of the regression line is 11.7585. And S is the standard deviation of the residuals. It's the standard deviation, period. But when it asks you for the standard deviation of the residuals, that's what you want to plug in. Okay, so now I think I'm ready to look at the graph. So I have my scatter plot and then the graph of my regression equation. So now I want to find all of the y hats. Probably the easiest way to do this is to look at the table. Okay, so what do I have here? 57. Now you can also calculate this. That might be easy. And the other problem with the table that they give you is not in numerical order, which is kind of annoying. Okay. Went too far. Okay, 57 is 772.7. So the residual is 1050 minus 772.7, which I get 277.3. And then you just do that for the rest of them. So what is 28? I don't want to scroll through all that. So get out of here. Go to my calculate menu. Oops. Calculate menu. Calculate the residual, the y hat for 28. Is that 431.7? So my residual is 428 minus 431.7. So it's negative 3.7. What's the value at 26? Second, calculate value 26, 408.1. So the residual is. Alright, so. I don't think it asks you to find all the residuals. How many residuals does it ask you to find? Ask you to find any? Let's find out. There's test statistic. Isn't it? Okay. It asks you to find the residual for the first point. So we did that, didn't we? The residual for the first point, the y hat was 772.7, and the residual is 277.3. And it asked me for the standard deviation, which was calculated when I calculated a linear regression test, which was 132.7644. All right, this is a graph of the residuals, but I swear I cannot figure out how they got this graph. And I have been pondering over this for how many semesters have I been teaching this? What the residual graph should be is the vertical axis should be the residual value. It should be y minus y hat. And the horizontal axis should be the independent variable. So in our case, the number of stories in these buildings. And that is not the number of stories in this building. And I'm not sure what that is, but the points look pretty much like the residual graph. So if you were to calculate all these residuals, which I did, and you were to plot that versus the independent variable, which I did, you'll get a graph that looks very similar to this. All right. So what about this graph? Well, first of all, can I use a linear regression on it? And the answer is yeah, because the residuals are fairly randomly dispersed. And randomly dispersed, I mean, it's like it's about the same number above the line that's y equals 0 as below. So it's pretty spaced out. And they just kind of randomly on there. So is the graph of the residuals, do you see any pattern? Okay, do you see what's called an outlier? Well, let's talk about outliers and we'll come back to this. Because there is an outlier on this graph. It just may not be the one you think it is. Okay, so we'll come back. And like I said, I'm not sure where they got that graph. I graphed it and it looks very similar, but I mean, very similar, but that horizontal axis is incorrect. I should write the person who wrote the question and ask it. All right. So let's test the significance of our correlation coefficient. Now, the problem we just looked at in section 12.6, they test the slope. So there's two hypothesis tests you can do. You can do a hypothesis test to see if your correlation coefficient is sufficiently large to use a regression. You can also do a test to see if the slope is sufficiently away from 0 to do the test. Can you see how those are both the same thing? If the slope of the line is 0, it's horizontal. Can I use a linear regression on a horizontal line? No. If the line is horizontal, its correlation coefficient is 0. So if you have a horizontal line, your correlation coefficient is 0, as is your slope. So you can do a test on the correlation coefficient, which is a row test, or you can do a test on the slope of the line, which is a beta test. They're the same thing, basically. And you can see in your linear regression test, you got what? Rho beta equals 0, greater than 0, less than 0. Okay? We perform a hypothesis test of the significance of the correlation coefficient to decide whether the linear relationship in the sample data is strong enough to use the model the relationship, to model the relationship in the population. So is my correlation coefficient strong enough that I can actually take my regression equation and do predictions about my population? Because my regression equation comes from a sample of my population. So if the relationship is strong enough, I can use it to predict things about the population. The symbol for the population correlation coefficient is the Greek letter rho. It's that kind of pretty P, but it is the Greek letter rho. Rho is the population correlation coefficient, which we don't know. And R is the sample correlation coefficient, which you calculate using the linear regression test. The hypothesis test lets us decide whether the value of the population correlation coefficient rho is close to 0 or significantly different from 0. If it's significantly different from 0, we can use our regression equation to do predictions. So your null hypothesis will typically be that rho is equal to 0 or beta is equal to 0, depending on which test you're performing. It'll give you the same p-value, by the way. One you're just looking at is the slope 0. And the other one you're looking at is the slope 0. So I'm not quite sure why there are two of them. I'm sure there's a reason, but the statistician doesn't know that right off the top of her head. And the alternative hypothesis will typically be that rho isn't equal to 0. So what's this mean? The null hypothesis that the population correlation coefficient is not significantly different from 0. There is not a significant linear relationship between X and Y. The alternative says the opposite, that there is a significantly different correlation coefficient is significantly different from 0. So there is a significant linear relationship. Drawing a conclusion, you check the p-value, just like we've been doing in hypothesis testing all along. If the p-value is small, you're going to reject the null hypothesis. If the p is low, the null must go. If the p-value is large, you cannot reject the null hypothesis. So if the p-value is small, there is a significant linear relationship between your X and your Y. If your p-value is large, there is not a significant relationship between your two variables. And we typically use alpha as 0.05. It's fairly typical of all the hypothesis tests we conduct. We're not using method 2. I dropped that from the slides because there is not one single problem in the homework that uses method 2. So I just dropped it. So what are we going to do? We're just going to compare the p-value to alpha. We're not doing. All right. So let's go back to your homework. Well, actually, let's go back to this problem that we did earlier. Let's look at this one. If we were to say that the null hypothesis is rho is equal to 0, and the alternative hypothesis is rho is not equal to 0, or the slope is 0, beta is 0, or beta is not equal to 0. Let's run that test again. I do believe we had not equals selected, but let's just look at it again. Okay, I got greater than, so I'm going to change that to not equal to. If it'll let me, come on. Oh, because I'm in the wrong place, you dummy. I probably shouldn't say that. I did. And got it caught on recording. Okay, enter. Okay, so testing the hypothesis that beta and rho are not equal to zero, the slope's not zero, the correlation's not zero. Let's calculate a p-value. So the p-value is 0.00004. P-value low, the null must go. So what's your conclusion? There is a significant linear relationship between these two variables. So going back to your problem. Statistic is 8.05911, correct? Yeah, again, you're saying, look at this, they're saying slope is not zero, so that's why this is a beta test. I don't even think they gave you rho as an option. So the beta null hypothesis would be that the slope is zero. The alternative would be that the slope isn't zero. We just did that calculation. The test statistic is 8.05911. The p-value was 0.00004141. So we reject the null hypothesis. So there is enough evidence to conclude that there's a significant relationship between these two variables, so the slope is not zero. Again, does it matter that we're testing beta or rho? No. We conduct the same test, we get the same p-value, no matter what we do. All right, outliers. So an outlier is a data value that doesn't fit the pattern. And typically we say it's an outlier if it's beyond 2 standard deviations of the regression line. Or is it 2 standard deviations beyond the residual? Either one of those, we would consider it an outlier. So why do we get outliers? That's something you have to figure out. So the first thing you're going to do is you're going to do your scatter plot. You're going to find your regression equation. You're going to graph your regression equation. Then you're going to look at your data values. And then you're going to graph your regression equation +2 and your regression equation -2 standard deviations. And you're going to see if any points lie beyond those 2 lines. If they do, that's an outlier. And then you're going to investigate why did it happen. Outliers are observed data points that are far from the least squares line, the regression line. It is possible that an outlier is a result of erroneous data. You just took the data incorrectly. That can certainly happen. Other times, an outlier may hold valuable information about the population under study and should remain included in the data. It might show you, believe you me, I am an outlier. Because I'm 6 foot tall and I'm a woman. I am an outlier. I am like so far out, like 6 standard deviations out from the average height of women in the United States. So am I insignificant? Should you not take my data? And the answer is, of course not. I exist. So my data is important. But I'm an outlier. Why am I an outlier? Because I had grandparents and uncles that were pretty tall. So that genetics came down to me somehow or some way. My entire family's tall. My sisters are tall. My brother is tall. My dad was tall. So there's reasons why I'm tall. I have cousins that are as tall as I am. Female cousins are as tall as me. So it kind of worked out that way. But I shouldn't be discarded because I'm an outlier, and I am big time an outlier. The key is to examine carefully what causes the data point to be an outlier. We can guess at outliers by looking at a graph of the scatter plot and best fit line. However, we would like some guidelines as to how far away a point needs to be in order to be considered an outlier. As a rough rule of thumb, we can flag any point that's located further than 2 standard deviations above or below the best fit line. The standard deviation used is the standard deviation of the residuals or the errors, which is that S, the value S, when you calculate the linear regression test. So it is calculated for you. We can do this visually in the scatter plot by drawing an extra pair of lines that are 2 standard deviations above and below the best fit line. Any data points that are outside this extra pair of lines are flagged as potential outliers. On the TI, on our calculators, this is very easy to do. As we did with the equation of the regression line and the correlation coefficient, we'll use technology to calculate the standard deviation for us. Using the linear regression t-test with this data, scroll down through the output screens to find S. S is the standard deviation of the residual. That is what it is. Okay. If you choose to delete an outlier, you have to state that as a researcher. I deleted this outlier because the data was collected erroneously. Whatever you have to do. But if you actually delete one, you have to tell us why you deleted it. All right. We're going to go back and look at the example that we've been playing with our buildings. Okay, so my graph is the graph of my scatter plot and my regression equation. So do I have an outlier? Visually, I'd say that one. What would you say? Visually, does it look like that one? So I am going to graph a line that's 2 standard deviations above this line, and I'm going to graph a line that's 2 standard deviations below. All right, are you ready? So we go to our y equals. Maybe. There we go. There's my regression line, and I'm going to go down to y2. And I'm going to type in y1, that equation above, plus 2s. Okay, so how do I get there? I'm going to go to my variables menu. What a wonderful menu it is. I'm going to go over to my y variables. I'm going to go to my function variables, y1, enter. And so it takes the y1 and puts it back into my y equals screen. Now I'm going to add to it plus 2 times the standard deviation. So I need to go find S. So I'm going to go to my variables menu. Number 5 is statistics. And I'm going to find S. Don't have to scroll a minute. Oh, not going to find it there because I need to go over to my tests. That S comes from the linear regression t-test. So it's going to be found in variables, stats, tests. You see S? There it is. Number 10. So we put enter. So now what's it going to graph? The regression line plus 2 standard deviations. So it's going to graph the line above. Let's just quick look at that. Ah, is that point an outlier? I think so. Okay, let's graph 2 standard deviations below. So go back to y equals, go down to y3, and repeat the process. So go to your variables menu, your y variables menu, function, number 1. Now we're going to subtract. Wouldn't it be nice if you could cut and paste? Minus 2 times S. So we're going to go back to our variables menu, to our statistics variables, over to our test, and find S. Oh. A little whack, a little crazy there. It'll let me go over. All right, maybe it'll let me. Okay. Try this again. Variables. Statistics. Test. Number 10. There we go. So on my calculator, since it's color, you get red and black. It doesn't really matter. Okay, that appears to be an outlier. That point right there looks to be an outlier. And I can figure out what point that is by turning on the trace. So go over here to trace, and it pops right onto that point. So what's my outlier? 57, 1050. Seven 1050. So on that first question in section 12.6, it tells you the first point in the table, what's the residual? We calculated that. The residual for the first point in the table was 277.3. We calculated that. What's the standard deviation? Your calculator calculated that for you. That's S. That is the standard deviation of the residuals. Is calculated when you calculate the linear regression t-test. Is this an outlier? And the answer is yes. Why is it an outlier? Because it's more than 2 standard deviations. So it's more than 2 standard deviations above 0. So what would be 2 standard deviations? 264, it's 277. So it is an outlier. Did we show that from the graph of the regression equation that it is also an outlier? Yes. So why do we have a building that's 57 stories high, that's 1,050 in height? Is that actually how tall that building is? Or did we make a mistake in the measurement? Is there some kind of error in the measurement? Or is it truly a 57-story building that's 1,050 feet high? I would have to investigate that, wouldn't I? And if it's an outlier that's true, if that's a real data point, then you can't delete it. If it's an error in your measurement, then you could, as long as you tell the people you present your data to, hey, I made a boo-boo on that data point, I deleted it. All right, let's do one last example. What time is it? We might have, I think we only have time for one. Yeah, let's come back to this one. I want to look at this problem. This is problem problem 4 in 12.6. And the reason I want to look at it is because we kind of threw you a curve. We all of a sudden gave you different information than what we've been giving you before. So I thought we'd take a quick look at it. Body frame size is determined by a person's wrist circumference in relation to height. A researcher measures the wrist circumference and height of a random sample of individuals. The data is displayed below. So we have a scatter plot of wrist circumference versus height. So the independent variable is the wrist circumference, and the height depends on what the wrist circumference is. So the first thing it tells you to do is to write the regression equation, y hat equals. So you need to be able to find from the data they give you, the tables they give you, what is the y-intercept and what is the slope. Now they tell you what the intercept is. So that bottom table, it says intercept. The coefficient is 38.4771. So the first value in my regression equation is 38.4771 plus the wrist is the slope, because for every inch larger your wrist is, your height grows by 4.5964 inches. So that is what the slope is. So the slope is 4.5964 times x. So that is your regression equation. What is the correlation coefficient? Well, r squared is 0.6115. So the correlation coefficient r is the square root of that. So I take my handy dandy calculator out and I take the square root. What's the coefficient of determination? Well, they give me that because I just circled it. So r squared is the coefficient of determination. It is the 0.6115. Use the equation of best fit to predict the height of a person with a wrist circumference of 6 inches. So what do? You plug in 6 for x, you multiply that by 4.5964 and add 38.4771. So it's a plug and check. Plug in 6 for x and see what you get. One of the points on the scatter plot is 6.4, 75.1. Calculate the residual. So what do you have to calculate? You have to calculate y hat. So y hat is 38.4771 plus 4.5964 times 6.4. And I had that written down somewhere. I get 67.8946. Is that what you guys get? So what's the residual? The residual is y, which is 75.1 minus what we predict it should be. So the residual is the actual data value you get minus what your regression equation predicts it should be. Whatever that's equal to. I get 7.20594. All right, what else? The mean. It just throws you off for some reason. It says, okay, on this date, yeah.
Why did you just use the first, like, point, the 6.4, because it says comma 75.1.
That's why. X is 6.4. So Y, the actual data value you took, someone's wrist was 6.4 inches in circumference and their height was 75.1 inches. That's the data value you took. Your line predicts that someone with a 6.4 inch wrist should be 67.9 inches tall. So what's the difference there? That's the residual. The difference in what you get when you take the data minus what you get when you predict it using the linear regression line. Okay. So if the mean wrist circumference for this data is 6.997, so all the X values, because you're taking ordered pairs, wrist circumference versus height, X is wrist circumference, Y is height. The average of all the X's is 6.997. Predict the mean height then. I mean, you're certainly not going to be able to find all the Y's to add those all up and find the mean Y. So what do? You plug the 6.997 back into your regression equation and find the predicted mean height. And it says, when predicting heights, what's a typical error using this linear model? Well, they give you the standard error. The standard error is what, 3.4469? Take that off your table and plug it in. Now, the only other thing about the homework is the scatter plots. And I had a difficult time. The scatter plot I did just fine and dandy. The regression line, I had problems getting my regression line correct. Have any of you done this yet? Are you perfect? Are your regression lines perfect? Like on this one, I had to draw it twice to get that regression line. But this one, this is the one that we've been doing all along, the 57,050. So 57, that's about 55, that's about 57, 1,050. That would be right there, maybe. And oh, I didn't see, I picked the line. I picked the point. Always got to make that mistake the first time. So I did pretty good at plotting the points. But drawing the regression line, I had some difficulty with. So if it counts it wrong, go down there and hit the ask my instructor and say, would you check my regression line? And if it looks good to me, I'll give you credit. Don't sit there and do this over and over and over again. Plot your points the best you can plot them. Draw the regression line, eyeball it as best you can. And if it counts it wrong, send me and ask my instructor. Would you, please? And I will give you credit for it. There's no reason to get the, I said, this one I drew a couple of times to get it to look pretty. All right. Let's do this one. I think we have time. All right, so we've got 8 minutes. Let's see how far we can get. So in this particular problem, they give you a set of ordered pairs. So the first coordinates, the first numbers in your ordered pairs are your X's. And the second numbers are your Y's. So you're going to put all the first components, the first numbers in a list. And you're going to put all the second numbers in a list. And then you're going to calculate a regression equation. And just eyeballing this, my first inclination would be that the 721 is an outlier. I bet I'm wrong. What do you bet? I think it's actually the 412 is might be the outlier. I can't remember. Let's find out. Okay, so I'm gonna get out of here. I'm gonna go run a linear regression test on my data. And I put my data in L5 and L6, which is nothing for you, but that's where I'm gonna test it. L5 and L6. And I don't really care about the test right now. I'm just gonna calculate this. Okay, so I have it calculated. So now I'm gonna go look at my graph. So I'm gonna do a zoom 9. That should be in there. Oh, I got two in there. What do we got in there? Is that my regression equation? Is that what you guys got? B 2.89 and I mean A is 2.89 and B is 2.27. Is that what you guys got? The graph looks weird. It should be correct. It should be correct. I don't know why it's doing that. Type it in again. Maybe it's remembering the previous F's. I don't know. Did your graphs come out okay? Did they look funky? I don't know why it's doing that.
That's the plot, it doesn't have a line through it at all.
Well, that's annoying. I don't know why it's graphing it over there. I've done something incorrect. It should be Purdy. What did you guys get for S? I don't know why it's drawing 3 lines. Well, I know why it's drawing. It should draw 3 lines. I don't know why it's drawing one on top of the other. I'll figure it out and send you a message in Blackboard. I can't figure out what is that what yours is doing too? Anybody got 2 pretty lines, one above and one below? I don't know what I'm doing. I could stand here and figure it out, or I can just send you what I did idiotic later. Are there any questions? Well, you've been stupendous. Thank you. One of the best classes I've ever had. I really appreciate it. If you have any questions, I'll be around. I'll be around tomorrow. Be around all next week. So if you have any questions, feel free to send me a message or come by and see me. if I don't see you, and if we have one graduate, which I'll be yelling for. If I don't see you, hopefully I'll see you next semester around.